Up until this point, you have only measured angles in units of degrees. Degrees measurement is actually a pretty arbitrary measurement. We think it comes from the ancient Babylonians and their observation that it takes approximately 360 days for the Earth to revolve around the sun. So in mathematics, it's not an exact measure. Radians, however, is an exact measure, and it's used in all upper-level mathematics courses, so calculus and on. Another idea behind that is it's okay to have different measurement systems. For instance, in America, we might measure a length in inches, whereas if you went anywhere else in the world, they would measure that same length with centimeters. Takes a little while to kind of wrap your brain around, so please take your time, ask questions as we go through this. Obviously, not live questions, but after the fact, to make sense of this radian system. So I'm going to start with 3 circles. The fact that circles are similar allows this system to really take effect. So when I say similar, I mean they're all proportional. They're all with that same angle measure of 360, or in this case, the same radian measure, which we'll soon find out about. And if I look at this in this first circle, so the radius of the first circle, if I outline that in red, I can show you where this radian measure comes from. So all a radian measure is how many radii fit along the arc of the circle. So if I took that radius and I fit it along this arc, there'd be 1 radius. If I then constructed another radius here, this angle formed. There's 1 radius here. This angle form is going to be called 1 radian, or rad for short. So obviously, there's going to be some angles that are very obvious, I think, in terms of making sense of I'm across from 1 radius length. There's going to be some in-between angles we'll have to make sense of. And actually, these angles are going to include pi. This is where that number came from. So if I continue along this pattern, and I put another radius in, and 2 radians along the circle, if I looked at that angle, and then I get to 3 radians. And here's kind of an interesting little neat tidbit. If I extend this across this diameter, I notice that I have 1, 2, 3, and a little bit more in terms of how many radii fit along the arc. Well, if I think about 3 and a little bit more, I might think of it as the number 3.14. There's pi. So there are pi radians along half a circle, a semicircle. So if I continue this pattern, I now have 4 radians, 4 radii that fit across. Notice that play on language. 5, 6, and a little bit more. So just a little bit left over. So a full rotation around a circle actually gives you 2 pi. That's exactly where the circumference formula came from. So what it is the circumference is 2 pi times the length of the radius, and that gives you the length around the circle. So if I did the same thing with these other circles, I'm not going to waste your time and draw all that out, I'll notice that pattern appears over and over. It doesn't matter how long the radius is, it's still going to be proportional to the circumference. So I have 1 radius, 2, 3, almost hit that half circle. 4, 5, 6, and a little bit more, full circle. And with these, I drew in other angle measurements. So for instance, by connecting this length here, this arc length, and I'm looking at that angle created, that central angle created there, it is across from 2 radii. So then it's the angle measure itself would be 2 radians. I kind of made up some numbers for you to see that too. If we say the radius is 5, and now this arc around there is 10, all the angle is, it's the ratio of the arc length, which would be 10, divided by how long the radius is. 10 divided by 5 tells you that 2 radii make up that rotation of that angle, so we call it 2 radians. And this one, we had 3 radians. So we're gonna kind of go back and forth between something you already know, which would be degree measure, and incorporate this new radian measure. So with both of these circles, they have degree measure, they're different sizes, they have different radii, and we're gonna bring back arc length. So we did know arc length with S, so I did S, and then the 10 pi, again, we're comparing it to the entire circumference, so that'd be 2 pi r, so 2 times 5 is 10. And then again, we don't know any other angle measure, besides degree measure. So I did 60 out of 360, we cross multiplied. We can figure out the arc length fairly easily going through this formula. Now, if I want a way to find the radian measure, okay, and I don't want to have to draw out that little diagram every time and mess around with that, I can simply look at the arc length itself and divide the radius into it. I want to see how many times that radius divides into it. So what I did is I wrote that down, and I did it in terms of pi. We like things to be exact in upper level mathematics. So 5/3 divided by 5, goodbye to the 5s, they cancel. You have a 1/3, so you be pi over 3. And that's just our radian measure. Same thing on this other circle. Okay, I'm trying to show you that if you set up the arc length compared to the circumference, and that's equivalent to 60 degrees out of 360, yeah, the arc lengths might be different. This was 5/3 pi, this is 8/3 pi. But once I look at that ratio again, I still get the same radian measure, okay, which makes sense. These are both 60 degrees, so these should be the same measure in the other system. If you wanted to put this in your calculator, you could say, okay, pi divided by 3 is 1.047. That's what I put over here. If you've been looking ahead or looking to the side there. So it's saying that this length is a little bit more than 1 radius along the arc. So a little bit more than 5 and a little bit more than 8, which should make sense. If I talk about how many radii can fit along the circle, okay, semicircle is 3. Okay, so 180 divided by 60 is 3. Yeah, this is a little bit more than 1 radius. So in terms of a formula, you can use this formula. It's actually very straightforward, and it always makes sense of this radian rotation, this angle measure. So they use theta, which is a Greek letter, just denotes the central angle here. You're always trying to figure out how many radii fit along the circle. So it's the arc length divided by the radius. So it's about how many fit along the arc. Leave things exact as long as possible unless they ask you to round it. So again, if we go to the back, they're really making sense of this full rotation, where circumference coming from, etc. So it says what arc length S is traveled in a full 360 degree rotation. So one full rotation around the circle would be 2 pi r. And I denoted that the 2 pi is just your scale factor. Again, so I can fit 2 pi radians. So 2 pi radians, excuse my handwriting, it's a little sloppy here, around the circle. And in terms of length, whatever that is, you just multiply by the length of the radius. Again, they're trying to make sense of this. So they're saying if we use this radian measure, put it into our little formula, what's one full rotation? Well, 2 pi r is the full circumference divided by the radius. Those cancel, and you're left with 2 pi. And I think it's fair to say we should really put units on here. I kind of messed up by not doing that before. So radians. We're not talking about length. We're talking about a different type of angle measure. So looking down here, and again, please read through that information on your own. 2 circles, not talking about degree measure, kind of threw it out the window for a second. We want to know radians, and I hope this makes sense. I'm going to try to draw things out for you too for the visual. And using this formula, so the central angle in radians would be the arc length of 15 divided by the radius of 6. It says you get 5 halves, radians would be my unit. 2.5 radii are rotated. Let's see if that makes sense. Well, if I have 6 for that length, okay, another 6 for that length, so I'm at 12, and then half of a radius, 3, there's my 15. The next one talks about, it looks like that angle's bigger, to be honest. It's not going to be. Talks about comparing a length of 18 and 8. So I divide those. And it's 2.25 radians, or 9/4 radians. So let's make sense of that. So I have 8. I have another 8. Oh, I'm just going to extend that a little bit. 8. I have another 8, let's say. So I'm at 16, and then 1/4 of 8 is 2. That's where I get my 18 from. So in some ways, this actually looks simpler than degree measure. The last one I want to talk about is, say they gave you the radian measure. Could you find the arc length, or could you find the radius? Absolutely. Let's look at our proportion here. Going back to this formula, our radians, our central angle, is the arc length divided by the radius. In this case, I want to just manipulate this first to kind of show you what's going on here. This is the simple way to always find arc length if it's in terms of radians and the radius. You can let go of that cross multiplication kind of lengthy strategy to find the length at this point. So I went ahead and I just said, okay, if it's 0.38 radians and the radius is 14 inches, I multiply that together. That's how many radii 0.38 radii fit along the arc. So the length is going to be 0.38 of 14, ends up being 5.32 inches. So understandably, this is a really tough topic, especially with this format of not being able to talk to you face to face or answer questions. I think it's doable though. So please, please, please ask me lots of questions. I can find other resources and we'll go from there. And good luck.